In the previous video, we solved an equation that was quadratic in form, but had a cosine and a sine in it. So we had to use an identity for cosine squared, 1 minus sine squared, and substitute that so that all of our expressions were in terms of sine. Only then could we make our substitution and use t squared and t instead of sine squared and sine. But that's not the only time you might run into a place where you might need to either do a substitution or make a change to a function using one of the identities. In this case, I'm taking an example from your textbook because it's better than the even number of problems that I could find that would address the same thing. Here, I've noticed that this is the cosine of a double angle, so I could replace that with one of three different things. I can either make my left-hand side cosine squared theta minus sine squared theta equals cosine theta. Or I could make my left-hand side 1, oh, it's not 1, sorry, it is 1 minus cosine squared theta, so 2 cosine squared theta equals cosine theta. Or I can make it 2 sine squared theta minus 1 equals cosine theta. And I have those choices because the cosine of 2 theta has three different versions. The identity has three different versions. That's a 2. So I get to make a choice. In the first option, I've got rid of my cosine 2 theta, and I only have cosines of theta, but I have cosine squared and sine squared here. So now I'm not going to be able to solve this, at least in its current form, without first changing sine into cosine. I could do that. I would get cosine squared theta minus, I'm going to use parentheses here, 1 minus cosine squared theta. That's using the Pythagorean identity, equals cosine theta. That's going to give me cosine theta minus a negative cosine theta. So I'd have cosine squared. Cosine squared theta, I have two of those, minus 1 equals cosine of theta. Now if I subtract cosine of theta from both sides, I get 2 cosine squared theta minus cosine theta minus 1 equals 0. And now I'm ready to do a substitution. So that's one way to do it. It looks like I got these formulas backwards. That happens sometimes. Let me go look them up and make sure I write them down correctly. Yep, that's exactly what I did. So the left-hand side, if I'm going to make this adjustment using a substitute for cosine 2 theta, I need to make sure that I've written it down correctly. It's either 2 cosine squared theta minus 1 or 1 minus 2 sine squared theta. Okay, my apologies. I kind of decided to leave that in there. I could have edited it out, but I decided to leave it in there just to remind you that, looking formulas up is fine. Do make sure you do it and make sure they're right before you carry on. And also that it's fine to make mistakes as long as you know when you've made one and how to correct it. All right, so now if I look at, let's see, if I look at this version right here, I have the same thing here as I did at this stage here. So I have exactly the same problem now, the same, question to answer. In this case of the problem, I have a sine squared and a cosine. So again, I'm either going to have to change the cosine, which I'm not sure how to do that. I don't have an identity for just cosine except for 1 over secant. Or I can change the left-hand side. I can change this to 2 times 1 minus cosine squared theta. That's changing my sine squared to 1 minus cosine squared. And that gives me 1 minus, I'm going to distribute 2 plus 2 cosine squared theta equals cosine theta. And when I do my arithmetic here, I end up with 2 cosine squared theta minus 1 equals cosine theta. And I have the same again. Now, there's absolutely nothing wrong with just trying one and doing some substitution and getting where you're going. But by writing all three of these out, I was able to look at these and go, oh, this one's already in cosine. All I have in this equation is cosines. So all I need to do now is subtract cosine from both sides, and I have a quadratic. I don't think I'm going to finish this one because you know how to solve quadratic equations. This would be 2 cosine squared theta, subtracting cosine from both sides. I'm going to get minus cosine theta minus 1 equals 0. So now this that I eventually came up with is the same as this. And I would get the same thing if I did it here as well. So solving this quadratic equation means substituting t for cosine of theta, and then solving that quadratic equation, back substituting, and then finding all the values that satisfy that equation. That's good practice, but I don't want to take more video time doing that kind of problem because we've already done some. If we need more practice on this, we actually need to practice this, physically practice this some more, then we can find some time in class to do that. All right, that was actually example 15 from your textbook, and I did that one before I did example 14 because I want to point something out. In order to solve this problem, we had to convert the cosine of 2 theta, this double angle here, into one of its three forms. It turned out it didn't matter which form we used, but having converted it using an identity, we were then able to solve the problem. The next problem I'm going to do is example 14, and it also uses a double angle in the equation. So let's see how that pans out and how that's different from this approach. For this problem, your textbook says, notice that the left side of the equation is the difference formula for cosine. And sure enough, if you look at this right here, this is the cosine of the difference of two angles. And those two angles are x and 2x. So this is one approach to doing this problem. The problem is you do have to notice, and we're not always as comfortable or as familiar with these formulas as we might need to be in order just to say notice that this is equal to the cosine of the difference of the two angles x and 2x. So what I want to do is try a different approach for the same problem without noticing. Before I do that, I do want to make the observation that in order to solve the problem using this approach, I'm going to take this cosine of x minus 2x and rewrite it as cosine of, this is just combining like terms, negative x. Then I have to notice that this is an odd-even function kind of identity, and I also have to know that the cosine of negative x is equal to the cosine of x. So at each stage, the right-hand side hasn't changed, and the left-hand side has been modified. And so now what I have is the cosine of x equals the square root of 3 over 2. And that I can solve. Remember that the cosine is positive in quadrants 1 and 4. So you're going to find a solution for this problem in quadrant 1. And then you're going to have to remember that there's also a solution in quadrant 4. And then you're going to have to add plus 2 pi k to each of those. So that's the approach that the textbook took here, but it's based on a pretty big jump, I would say, at this point in your career, this observation, this recognizing this version, this form of a double angle formula. So I just wanted to point that out and show you how this proceeds, but now let's take a look at how we might do this a different way. Our job is going to be to try to get everything in terms of cosines or everything in terms of sines. Now that's not necessarily the only way to do it, and in fact I think we're going to run into some trouble doing that, so I'm just going to kind of play this one by ear and see how it unfolds. I do notice that I have a double angle here, and that at least I think you should be able to do at this point, recognizing you have a double angle, and use the double angle formulas to convert one form of this equation into another. I'm going to start by changing the cosine of 2x into, again, I have three different options here. I'm going to leave it blank just for the moment. And then I'm going to add the sine of x times, and I might try changing that as well. I haven't really decided yet. That's all going to be equal to the square root of 3 over 2. Now, with the sine of 2 theta, there is only one form of that formula. That's the sine of 2 theta is equal to 2 sine theta cosine theta. So this term now looks like this: 2 sine squared theta cosine theta. And I still have to figure out which form I'm going to use here and then simplify this side. Here I've got a sine squared and a cosine. Here I've got a cosine. So depending on how this term pans out, I could factor out a cosine. If I have a cosine and a cosine, I could factor that out. With that in mind, the form that I'm going to choose for the cosine of 2x, the form of the double angle formula that I'm going to choose, I want it to contain cosine. Or I want this cosine to remain in place so that I can factor it out of both this term and this term. So I want this cosine to stay in place. But the form of the cosine of 2 theta that I want to use, I could use cosine squared minus sine squared. I could use 1 minus 2 sine squared. That would give me a sine squared in this term as well. Or I could use 2 cosine squared minus 1, and that would turn everything on this side into cosines. In fact, it's really not clear which one we should use. So I'm actually going to start with the cosine squared minus sine squared version, and we'll just see where that leads us. Cosine squared of x minus sine squared of x is another way to write cosine of 2x. So I've just converted the cosine of 2x into cosine squared minus sine squared of x. Now what I'm going to do is distribute that cosine. So I have cosine cubed of x minus cosine of x times sine squared of x. And now if I look at the entire left-hand side all together, I have at least one factor of cosine in each term. So I'm going to factor out cosine x. That leaves me with cosine squared of x minus the sine squared of x plus 2 times the sine squared of x. And that's still equal to the square root of 3 over 2. Now I'm going to combine like terms. I have, sorry, not that one. I have minus the sine squared of x plus 2 times the sine squared of x. So I have cosine of x times cosine squared of x. And when I combine positive 2 of these plus negative 1 of these, I get plus 1 of these being sine squared of x's. And I hope you've seen it. Cosine squared plus sine squared equals 1. So now I can rewrite this as cosine of x times 1, I don't really need that, but I'll put it there anyway, is equal to square root of 3 all over 2. I'm asked to find, I'm asked to solve this on the interval 0 to 2 pi. So I also need to figure out if I have more solutions here. And since all students take calculus, and since my cosine is a positive value, I may have another, in fact, I do have another solution in quadrant 4. This is my reference angle, pi over 6. I'm going to take another reference angle of pi over 6 and go into quadrant 4. Now the easiest way to name this angle, since this is pi over 6, this is probably negative pi over 6, right? So we just call that negative pi over 6. However, we're asked to find answers in this interval. Negative pi over 6 is not in this interval. So we need to find a different name for this angle. And that's easy enough. All I have to do is go around the circle until I get there, and wherever I land, that's my answer. This is coterminal to my answer. So what is my answer? Well, all the way around once would be 2 pi, and that's 12 pi over 6. So if I take 1 away from that, that's 11 pi over 6. So my second solution is 11 pi over 6. And in this case, because I'm only looking for answers in the interval 0 to 2 pi, those are my answers. I don't need a plus 2 pi k here. Now, mostly because I'm curious, I'm going to redo this problem with a different identity for the cosine of 2x. So take a mental image of this screen, if you will, because if I find myself with this expression or this expression, I'm not going to finish the problem because I'll know that if I get from here to, say, here with a different identity, then I've arrived at the same sort of stopping point, right? I don't need to finish the problem to know my answers are going to be the same. So I'm going to erase back to here. I'm going to erase this identity and I'm going to replace it with a different one. This time, let's try 1 minus 2 sine squared of x. That's another way to write the cosine of 2x. Okay, again, I'm going to distribute the cosine of x times 1 minus 2 times the cosine of x times the sine squared of x plus 2 times the cosine of x times the sine squared of x equals root 3 over 2. Now notice that this is minus 2 cosine sine squared and this is plus 2 cosine sine squared. So those actually cancel and I'm left right away with cosine x equals root 3 over 2. And I know how to find the solutions to that. Those were pi over 6 and 11 pi over 6. So that's really interesting. It took us a lot fewer steps to do it that way. And that just goes to show you, sometimes there's a little bit of guesswork involved. All right, just for fun, I'm going to do it with 2 cosine squared of x minus 1. So if this time I replace this with 2 cosine squared of x minus 1 and distribute, I get 2 cosine cubed of x minus cosine of x plus 2 sine squared x cosine of x equals root 3 over 2. I still have a common factor of the cosine of x. I'm going to factor that out. I get 2 cosine squared of x minus 1 plus 2 sine squared of x equals root 3 over 2. Now I have cosine of x times, looks like I have 2 cosine squared of x plus 2 sine squared of x minus 1, just reordering the terms there. And that turns out to be, if I factor that 2 out, I get cosine squared of x plus sine squared of x. And then I have a minus 1. Have you seen it yet? I have 2 times 1 minus 1. And 2 times 1 minus 1 is 1. So in this case, it doesn't matter which of the 3 versions of the formula for the cosine of 2x you use, you end up at the same place. You end up with the same result. It turns out that the 1 minus 2 sine squared version was the one that produced the required the fewest number of steps, but I didn't know that. I couldn't tell that just by looking at it. So sometimes you just have to start with something and give it a shot. All right, this video is longer than it really needed to be because I kind of wanted to play around with those other 2 options, but I think that's enough for here. Let's take a look at the next topic.